Hey apes. This is the second part of our non-renewable energy resources presentation. And in this presentation, we're going to cover fossil fuels and nuclear resources. We're going to begin with coal. Coal is a solid fossil fuel, and it's formed primarily from plant remains that were fossilized millions of years ago. So we're going to talk, as we talk about fossil fuels, they come from different types of fossilized materials. Coal is primarily plants. It's abundant in many parts of the world, including abundant in the United States. And coal is relatively easy to extract, handle, process, and transport. The largest proven coal reserves are found in the United States. Yay, we're number one. Russia, China, and India. But the countries that produce the greatest amount of coal are China, the US, India, and Australia, which of course isn't on the list of largest proven coal reserves, but they actually produce a fair amount of coal. Coal is now the second most common fuel for electricity generation in the United States. This actually began in 2016 was the first year that natural gas outpaced coal in terms of electricity generation. Prior to that, coal was the number one fuel for electricity generation. Now it's number two. There are four main types of coal, and they're classified by their age, their exposure to pressure, the moisture content, the sulfur content, and how much energy they provide. The four main types of coal are lignite, subbituminous, bituminous, and anthracite. And on the next slide, we're going to talk about the energy and other characteristics of each one of those, so don't fret. Peat is a precursor to coal that is burned for fuel in some parts of the world. So if you were talking about how long stuff has been in the ground, peat is partially decomposed plant matter that has not yet fossilized. It has not yet turned into coal. Peat would be the precursor to coal. Then it would become lignite, subbituminous, bituminous, and anthracite. And here's a little graphic on the different characteristics of coal. So coal, again, is classified with two ways: the carbon and the energy content and the moisture content. Also along sulfur content goes along with that as well. And this is not shown on this particular graphic. So if you follow the flow chart down, right, you have low rank coals and what they call hard coal. Low rank coals are lignite and subbituminous. Globally, those make up about 48% of the global coal resources. Hard coal is about 52% of global coal resources, and hard coal is classified into bituminous and anthracite. As you can see here, bituminous is the most common type of coal globally. It's 51% there. Lignite's been in the ground the least amount of time. Subbituminous, it has been in the ground longer than lignite. Bituminous longer than subbituminous. And anthracite is hard coal that's been in the ground for quite a long time and been subjected to a lot of heat and pressure. So what do we do with each of these types of coals? Well, lignite coal is burned mainly for power generation. It's 20% of the world's coal is lignite. Although it has a high sulfur content, it's relatively easy to get, so we burn it to create electricity. Subbituminous coal and bituminous coal, here we go, following these two down right here. Subbituminous coal is used for power generation. It's also used in cement manufacture and for industrial uses. Bituminous coal is used thermally for steam coal, also for power generation. The same thing that subbituminous is used for. It is also, however, used in metallurgical applications as coking coal for the manufacture of iron and steel. And that is because it burns at higher temperatures and it gives a higher BTU output. So, and they need that for the manufacture of iron and steel. Anthracite coal is the rarest kind of coal. It's been in the ground the longest. It's hard. It's got a low sulfur and a low moisture content. And it, when it's burned, it has a high BTU output. Anthracite coal is used in domestic and industrial applications, including as a smokeless fuel. You can actually burn anthracite coal directly to produce heat. It is not largely used for power generation just because it's rare. And a lot of the anthracite coal has already been mined out. That was kind of like the the premier source of coal, and we used that up long ago. So when you get it, it's used largely as smokeless fuel. It's sometimes also used in metallurgical applications for the creation of iron and steel. Okay, so let's talk about advantages and disadvantages of coal. Advantages of coal are that it's energy dense. That means that for every unit volume, like let's just say grams, you get a lot of energy from coal. It's also plentiful worldwide, including in the United States. The US has the world's largest proven coal reserves, so there's a lot of it. It's relatively easy to extract via surface mining. Technological demands and economic costs for surface mining are also low. Coal is easy to handle and it's easy to transport because it's solid. Once we get it out of the ground, it's easy to deal with. Coal needs very little processing before use. The way that you dig it out of the ground is largely the way that you burn it. And infrastructure to transport and use coal in the United States is extensive and it's already been built. We've been using coal as a fuel source since the Industrial Revolution, which largely began in the US in 1850. So we know how to deal with coal, and we know how to deal with coal well and easily. Disadvantages of coal, however, are numerous. The tailings from surface mining of coal are extensive. That's the leftover stuff. Water running through tailings of a surface coal mine create acidic mine drainage. Subsurface mining of coal, what I call the Scooby-Doo type of mining, and we've got like room and pillar and longwall mining. We've talked about those before. Those types of subsurface mining are more expensive and more dangerous than surface mining. And it comes along with the same problem of acidic mine drainage. When water seeps through subsurface mines or the tailings of surface mines, it becomes acidic due to the sulfur content of the stuff left behind. And acidic mine drainage has lots of negative environmental consequences. We also end up with acidic precipitation from sulfur oxides when coal is combusted. When coal is combusted, the sulfur combines with water vapor in the atmosphere to create sulfuric acid, which produces acidic precipitation, which has a lot of negative environmental consequences. Heavy metals such as mercury, lead, and arsenic are also released when combusted. Especially downwind of coal-fired power plants. So we get heavy metal contamination in in soil, in groundwater, and in crops if they're downwind of a coal-fired power plant. Particulates are released when combusted. Fly ash, that is the ashy particles that come off of coal when it's burned. That stuff needs to be taken out. It can be taken out in a number of different ways. We've talked about baghouse filters. We've talked about scrubbers, wet scrubbers, and things like that take out that kind of stuff. However, they are still released when combusted, and even with cleaner technology and smokestack scrubbers, we still get particulates released. Nowadays, coal is washed in a combination of chemicals to make it burn cleaner, but the chemical washes have not been tested for toxicity, and there have been numerous incidents around the country where those chemical washes themselves have gotten into groundwater, polluted groundwater, and created an environmental pollution. We also have the problem of coal ash. Coal ash is left over from the combustion of coal. It's usually mixed with water and it's stored on site at coal-fired power plants. These coal ash receptacles can leak, and they have leaked in many cases. Coal ash leakage is a huge problem. When it does leak, it causes massive environmental pollution. So not only do you have that sludge from coal ash, but there's a lot of heavy metals in that sludge as well. And it is a massive, massive problem when those holding tanks bust. And there's a case study on that in your textbook. Petroleum. Petroleum is a fluid fossil fuel that's a mixture of hydrocarbons, water, and sulfur. It's primarily the fossilized and liquefied remains of phytoplankton from millions of years ago. So phytoplankton is not a plant. Phytoplankton is a type of algae, primary producer in aquatic ecosystems. And remember, if you think back, coal was the fossilized remains of plants. Petroleum is the fossilized and liquefied remains of phytoplankton. The liquid nature of petroleum makes it an ideal fuel for transportation, and indeed that's usually what it's used for. Petroleum is accessed via drilling, and it's transported via pipeline or via tanker truck. Petroleum contains natural gas. Natural gas can be flared off as a waste gas or captured and used as a fuel in its own right. So it just depends on where you are in the world that this petroleum is being drilled for and what people want to do with the natural gas. If the infrastructure is in place to capture the natural gas, then it's usually captured. If it's not, it's usually flared off. Liquid petroleum in its unrefined state is called crude oil. Crude oil can be refined in a cracking tower into other compounds. A cracking tower is a part of an oil refinery. And this cracking tower refines crude oil based on the boiling points of its different constituents into tar, asphalt, gasoline, diesel, kerosene, and naphthalene. There are about 150 active oil refineries in the United States. Petroleum is the basis of an industry that we call the petrochemical industry. So petrochemicals include things like plastics. Literally everything in your life made of plastic comes from petroleum, which is kind of crazy because when you look around you, like just look where you're seated right now, you can probably point to at least 10 to 15 things that are made of plastic or have plastic components. Every single one of those is based on fossil fuels. So plastics, lubricants, cosmetics. Yes, ladies, the stuff you put on your face is usually petroleum based. Pharmaceuticals. Many of our drugs are also made from petrochemicals and cleaning products. So petroleum is very versatile and it's used in lots and lots of different ways. The top petroleum producing countries in order are Saudi Arabia, the United States, Iran, China, Canada, and Mexico. These 7 countries combined produce about 1/2 of the worldwide production of petroleum. Advantages and disadvantages of petroleum. So advantages are that petroleum is extremely convenient to transport and use. It is energy dense, just like coal, meaning that per unit volume, it produces a lot of energy. But it's cleaner burning than coal. And it's cleaner burning in terms of particulates, in terms of carbon dioxide, in terms of sulfur and heavy metals. Does it have those? Yes, it does, but it's much cleaner than coal when burned. And it's ideal for transportation uses because it is liquid and it's easy to transport and use. So what are some disadvantages of petroleum? Well, it still contains trace amounts of sulfur and heavy metals, although much of these can be removed during the refining process. Refining oil is complex and it's dangerous. Refineries are also expensive to build. Oil can leak during extraction and during transport, and oil spills are difficult to clean up and they are highly environmentally damaging. Oil pipelines, if oil is being moved by pipeline, oil pipelines often traverse environmentally sensitive areas. And as we've seen over the past year, they also can traverse areas that are culturally sensitive. In the case of the Keystone XL pipeline, a lot of these pipelines are going over land where people don't necessarily want them, and they can also be at times they're rerouted to areas where people do not fight the land process, or where developers think that people will not fight the pipeline process. That kind of backfired this summer when we were talking about some of the pipelines that people were trying to build and are still trying to build. So oil pipelines are traversing these environmentally and culturally sensitive areas. And guys, oil pipelines leak. They leak oil. It's a known thing. And so, people who have political means don't want them on their land. Additionally, flare-offs of waste natural gas and waste methane can cause human health problems. The flares have been linked to asthma problems, especially in places like Nigeria. And flaring off of methane can contribute to global warming. Importing oil also raises national security risks. The Middle East is a oil-rich area, but the Middle East is also politically unstable. And so when we're talking about importing foreign oil, we're talking about dealing with countries that have questionable human rights records and, might not have the greatest commitment to democracy. So importing oil, you're dealing with iffy national governments. Okay, natural gas. Natural gas is the cleanest burning of all fossil fuels. Natural gas is mostly methane. The chemical formula for methane is CH4. There are smaller amounts of ethane, butane, propane, and isobutane in natural gas, but it's on average about 85 to 90% methane. Natural gas is extracted along with crude oil deposits, but it's also extracted via hydraulic fracturing or fracking in its own right. So natural gas is sometimes found on top of the liquid crude oil deposits, but there are formations where most of the hydrocarbons extracted are in the form of natural gas, and that's where fracking tends to come in. Currently, natural gas is the largest source of fuel for electricity generation in the United States. Natural gas is also heavily used in industrial processes. It's also used to make synthetic fertilizers and as a consumer fuel for cooking, heating, and operating gas-powered clothes dryers and heaters. So we use it directly in our homes as well. Compressed natural gas can be used as a vehicular fuel. And you'll see city buses. Here in Dallas, we see city buses that say CNG on the side. And underneath that says clean natural gas. But what CNG actually stands for is compressed natural gas. So those buses are running on compressed natural gas. LPG, which is liquefied petroleum gas, is similar to CNG, and it is a more common fuel source. So natural gas can be used as a vehicular fuel source as well. So what are some advantages and disadvantages of natural gas? Well, some of the advantages are that there's an extensive natural gas pipeline infrastructure in the United States, which means that natural gas can be readily supplied to consumers. And where pipelines are not available, LPG or liquefied petroleum gas can be supplied via tanker truck. Natural gas is the cleanest burning of all the fossil fuels. It emits almost no particulates or sulfur, and it's got about half of the carbon dioxide emissions of coal combustion. Disadvantages of natural gas is that it is mostly methane, and methane is a potent greenhouse gas. Methane traps about 25 times the heat of carbon dioxide. So one molecule of methane is 25 times more potent in terms of heat trapping ability than a molecule of carbon dioxide. Natural gas leaks during fuel extraction contribute to global warming. Fracking for natural gas uses large amounts of chemicals that haven't been tested for safety, and wellbore leaks may result in groundwater contamination due to these chemicals. Wastewater disposal from frac sites has also been linked to seismic activity. And when I say seismic activity, I'm talking about earthquakes. So when you hear people say fracking causes earthquakes, it's not the fracking itself that's causing the earthquakes. It's the wastewater disposal from the frac sites. In addition, something that I don't have on here is that fracking uses a fairly large amount of fresh water. Fracking uses water, and it uses a fair amount of it during the frac process itself. You're going to see a video that's embedded in the next slide that talks about how much water fracking uses. Now, it uses less than a lot of other processes, but in some of the areas that fracking is occurring, those are desert areas anyway, and so the fracking can actually have a significant impact on local water resources. Okay, so this is the video that I want you guys to watch, which is the first one, How Fracking Works, the TED Ed video. So if you'll go ahead and click on that, that's the video that I want you guys to see. How Fracking Works, TED Ed video, and it's been uploaded by this person named Mia Nakamoli. Okay. Let's talk a little bit about unconventional fossil fuels. So fossil fuels can be extracted from sources that what we call are unconventional. When we say they're unconventional, it means that they're not used very frequently, but they are used at times. So things like oil sands or tar sands. These are slow-flowing, viscous deposits of bitumen mixed with water, sand, and clay. Well, what the heck is bitumen? Bitumen is a degraded form of petroleum that is found in surface deposits. This is where oil has seeped to the top of a formation and it's been exposed to the air. So the light hydrocarbons have either been metabolized by bacteria or they've evaporated, which leaves behind a thick mixture of heavier hydrocarbons, which can be basically scraped off the top and refined. Oil sand and tar sand refining, there's a lot of impurities in this stuff. There's water, there's sand, there's clay, and all the bitumen has to be extracted from the surface impurities. It's a dirty process and you don't get a very clean product at the end of it, which is why it's not done very often. But Canada has a large amount of tar sands, and we are mining Canadian tar sands. Oil shale is another unconventional fossil fuel. Oil shale is sedimentary rock that contains solid hydrocarbons that can be mined and refined to produce shale oil. So it's basically sedimentary rock that is mixed in with these solid hydrocarbons. You can scrape it or you can mine it out, and then it's basically refined, it's burned to produce shale oil. Liquid coal or CTL, that's coal to liquid. CTL stands for coal to liquid. This is technology that can convert solid coal into liquid form for use as a liquid fuel. Because the U.S. has extensive, and by the way, this isn't actually new technology. It's been around since basically World War II. The U.S. has extensive coal reserves, and the use of this technology could actually eliminate our dependence on foreign oil. But that comes at a cost. This technology, the greenhouse gas emissions, GHG is greenhouse gas emissions, by the way, right here. Greenhouse gas emissions from the burning of coal to liquid or CTL fuel is basically twice that of conventional oil. There's a ton of greenhouse gas emissions from the burning of this liquid coal, and the environmental impacts of coal mining are much more severe than the environmental effects of oil mining, so oil extraction. So it's probably not a technology that we're going to invest heavily in. We could do it and it would reduce our dependence upon foreign oil, but it's pretty dirty technology, and it's not particularly, it's not got a great return on energy investment. Okay, let's talk about the Hubbert curve. So fossil fuels are a finite resource. They're not sustainable. So why are they not sustainable? Well, there's no way to limit our use of them to the rate at which they are formed. So the definition of sustainability is using a resource at the rate or below the rate at which it's formed. We can't do that with fossil fuels. Fossil fuels, although they're technically still being formed, they're being formed at a rate that's very, very slow. So there's no way for us to limit our use of them to the rate at which they're formed, which by definition means that they're not sustainable. As new extraction technology has been developed, concern has shifted away from the actual supply of fossil fuels available, which was our driving concern in the 70s and 80s, to the consequences of fossil fuel combustion, particularly in relation to global climate change. But we still need to talk about the Hubbert curve. The Hubbert curve is a bell-shaped curve. It represents oil use, and it projects both when the world oil production will reach its maximum and when oil will finally be depleted. It was developed in 1969 when this was kind of at the worry of when we were going to run out of oil was kind of at the forefront. The Hubbert curve uses upper and lower estimates. Peak oil is the point at which point on the curve at which half of the total known supply of oil is used up. And experts still debate whether or not we've reached peak oil or will be reaching it soon. But it doesn't really matter because the total number of years that we'll be able to use petroleum as our primary world fuel source, it is going to fall within a relatively narrow time window. It is a finite and non-sustainable resource. So it will run out at some point. There's a famous quote among energy experts: the Stone Age didn't end because we ran out of stones. So the Stone Age ended, right? Our use of stones as tools ended because better technology came along. We still had stones, but we recognized that making tools out of stones was not the best use of stones, and that better technology was coming along. So what fuel is going to replace our dependence on oil? We really don't know yet. And that's kind of where the forefront of energy research and development currently is. This is the Hubbert curve. This is an example of a Hubbert curve. So again, it shows the point at which world oil production would reach a maximum and the point where we will run out of oil. So if you take a look at this curve, remember I told you it's got an upper and a lower boundary. So here's our lower estimate right here, and here's our upper estimate. Okay. So the peak here, this is peak oil. The top here would represent peak oil. And where it goes to zero over here would represent where we're going to run out of oil. The red curve here, it says it's an estimate of the maximum that's on the planet but has yet to be resourced. So the blue line represents proven or known reserves, and the red line or the upper estimate is reserves that could possibly be there, but we don't know for sure. But at any point, you can see that peak, right? And the x-axis is time, is where 1/2 of the world's proven reserves have been, tapped out. Nuclear energy. Now, nuclear energy is not a fossil fuel, but it's included in the non-renewables because it is a crustal resource that has a finite supply. So electricity is generated from nuclear fuel via fission, nuclear fission. Fission is a reaction in which a neutron strikes a relatively large atomic nucleus. This is usually uranium-235, which is easily fissionable, which then splits into two parts, releasing additional neutrons and releasing energy in the form of heat. Like I said before, nuclear energy is considered non-renewable because its fuel, which is for the most part uranium and to a lesser extent plutonium, are crustal resources that are in a limited supply. The heat from fission is used to boil water to create steam, which turns a turbine, which powers a generator, which produces electricity. Yes, we are splitting atoms to boil water. And when I state that to APE students in that particular way, most of them are usually like, really? Yeah, we're splitting atoms to boil water. 1 gram of uranium-235, which is the most commonly fissioned isotope, contains up to 3 million times the energy in a gram of coal. And this, my friends, is why we use nuclear fuel as a energy generation source, because you can use just a tiny bit of it and produce a lot of energy. The byproducts of nuclear fission are waste heat and radioactive waste. And radioactive waste remains dangerous for hundreds of thousands of years, or possibly longer. We're not 100% sure. This is a schematic of a nuclear power generator. I've kind of put down here on the bottom what's going on. It's down here. Boop, boop, boop. So this is the containment structure right here. And this is where the reactor is actually located. There's the reactor core, and there's control rods in there. It's pressurized, by the way. So it's under pressure. So the containment structure contains the nuclear fuel rods, which contains the pelletized uranium, and it also contains the steam generator. So here we go. Here's our control rods, our core, and our steam generator. The uranium-235 is processed into pellets that are placed into the fuel rods. Fission is used to heat water within the containment structure. The water circulates in a loop, and here it is right here. This is the water circulation loop. See it? Okay. This loop passes close to another loop, and that's this loop that's right here. So here's our steam generator, right? So this loop, this hot water loop is heating up the water, right? That's coming in here. So this is our cooling water coming in here. Nuclear reactors produce an incredible amount of heat. And if we don't have cooling water circulating around them, then we end up with a nuclear meltdown. All right, so this is our heating loop, and this is the water that's coming in that's circulating around that heating loop that's getting heated up. So this water that's circulating around right here is what's boiling to produce the steam. I want you to notice that this loop, this closed loop that's circulating around the reactor where the hot water is, this water is radioactive, but it never comes into contact with the water that creates the steam. The water that creates the steam, that this loop flows into that steam generator, but the water never comes into contact. So the steam here created from that hot water is not radioactive. This steam is not radioactive. The steam goes into the turbine area. The steam turns the turbine. Here's our shaft right here. The shaft turns the generator, inside the turbine. It powers the generator, and the generator powers electricity. So once we're here at the turbine area, everything at this point is the same as a coal-fired power plant. The turbine turns, it spins the shaft powers the generator powers electricity. This right here is a condenser where the cool water is circulated to keep that water nice and cold so that it can flow around and keep the reactor core cool. And if you look right here, the heat is transferred in the process, steam is produced, which turns a turbine. Control rods, which are these guys right here, are inserted between the fuel rods to absorb excess neutrons and to slow or potentially stop a fission reaction. This is what controls the fission reaction. Without the continuous flow of water and the presence of control rods, the reactor would get too hot and we'd end up with a meltdown. Has this happened before? Oh, yes, it has. So let's talk about that. All right, so advantages and disadvantages of nuclear energy. Well, proponents of nuclear energy say, hey, nuclear energy is clean. And they're right. Nuclear energy produces absolutely no air pollution. In countries with limited fossil fuel resources, nuclear fuel and nuclear energy provides an option that allows the country to be free of imported oil. And this is a big deal. Imported oil is a pain in the bahootie for many reasons. Nuclear power plants are generally safe to operate under normal conditions. Uranium itself has an extremely high energy to mass ratio. You only need a tiny amount to power a reactor. So these are all advantages. Disadvantages of nuclear power is that power plants are expensive to build. Nuclear power plants, they need backup systems and they need extensive safety systems in place for them to be operational. The public perception of nuclear energy is very negative, especially in the United States. We've got and there's a reason for this we're going to talk about here in just a sec. But the public perception of nuclear power is negative, and people generally do not want nuclear power plants anywhere near them. There's also no good solution to the issue of radioactive waste. We currently do not deal with it well here in the United States. There's really no country that does deal with it well. In a lot of European countries, it is reprocessed and can be used again, but there's still not a great way to deal with it. Waste has the potential to be a national security risk because nuclear waste can be made into dirty bombs. So it has to be stored securely, and it has to be stored securely for a very long amount of time. If it falls into the hands of the wrong people, we end up with some dangerous stuff. Nuclear power plants create thermal pollution in nearby bodies of water. Nuclear power plants must be built close to water, and they use that water in order to cool the reactor. And so although they're not putting out radioactive water or radioactive material, they are putting out water that is artificially heated, and it's higher in temperature than it should be for the natural surroundings, which, if you remember, was also a drawback for coal-fired power plants. Uranium mining is highly dangerous, and the tailings of uranium mines are very, very, very dangerous. And again, so the last point is, although nuclear accidents do not happen frequently, when they do happen, there's really no such thing as a minor nuclear accident. Even small amounts of exposure to nuclear radiation can cause some damages, both human health risks and environmental health risks. So nuclear accidents are a big deal, and obviously that's a disadvantage. What nuclear accidents do you need to know about? You need to know about 3 Mile Island. 3 Mile Island happened in Pennsylvania, here in the United States. It happened in 1979. There was an operator error. The operators did not notice that there was a valve that was stuck that was not allowing cooling water to come into the reactor. This error led to a lack of cooling water circulation. There's 3 reactor cores. One of them overheated and suffered a partial meltdown. People around the area, this was a highly, and it still is, a highly populated area. People were evacuated, and boy, people were very, very panicked. They were freaking out. We're not exactly sure if there was a release of radioactive gases or not. There was possibly a release of radioactive gases. That was not confirmed. There were no known long-term or short-term documented human health effects, but the 3 Mile Island accident produced widespread fear, panic, and anger over nuclear energy and nuclear power in the United States. It was kind of the beginning of the end for nuclear power. Now, we do still have lots of nuclear power plants that are online, and about 20% of U.S. power electricity is currently generated by nuclear power plants. In fact, here in the DFW area, we receive a fair amount of our power from a nuclear power plant called Comanche Peak, which is about 60 miles away from Dallas. But there's a very negative perception amongst people and the general public for nuclear power. And again, one of the reasons for that is the 3 Mile Island accident. The next accident you need to know about was Chernobyl. It happened in April of 1986. It happened in an area called Pripyat, which is in the Ukraine. Chernobyl was actually the name of the power plant itself. The town was named Pripyat. So operators were conducting a unauthorized safety test, and they did some bad stuff that was totally outside the pale. They deliberately disconnected emergency cooling systems and removed control rods. Well, duh. When they ran the safety check, they ended up with a complete meltdown of the reactor core, which resulted in an enormous fire and subsequent explosions. 31 plant workers died immediately. 31 plant workers and emergency responders died immediately in the aftermath from acute radiation poisoning. And winds blew the radioactive fallout across Eastern Europe, which contaminated crops and contaminated soil and surface water. I will tell you that I remember Chernobyl quite well. I was in high school when it happened. And the USSR kept this a secret for a while. People did not know what was actually happening. Eastern European countries were registering high amounts of radioactivity, and they couldn't figure out why, because there had been no statement from officials in the Ukraine. It took over a week for officials in the Ukraine to actually come out and say that there had been a nuclear disaster. And by that time, the radioactive fallout was pretty extensive across Eastern Europe. Chernobyl was the largest nuclear disaster and is to date the largest nuclear disaster in history. So experts estimate that there was an additional, besides those 31 plant workers and emergency responders that died immediately from radiation, Experts estimate that there was an additional 4,000 radiation-related deaths in the Ukraine and across Eastern Europe due to nuclear fallout from Chernobyl. The Chernobyl, it was poorly contained. People did not respond. The emergency responders did not respond to it correctly for almost a week. Huge problem. And again, the largest nuclear accident to date. The third nuclear accident that you need to know about is Fukushima Daiichi, which happened recently in March of 2011. Fukushima is a prefecture in northeastern Japan. The actual town is Okuma. Okuma is in Fukushima Prefecture, and there was a nuclear reactor, the Fukushima Daiichi, and it was located on the coast. There was an offshore earthquake that created a tsunami. The tsunami wave came and it crashed into the plant, and it partially damaged the plant. It actually cracked one of the containment structures in one of the reactors. And seawater actually got in there. Safety systems properly shut down the fission reactions in the damaged reactor core. However, the damage from the tsunami had disabled the backup generators that ran the pumps that continued to circulate the cooling water. So even though the fission reaction was shut down, there's a lot of heat that still builds up, and the cooling water needs to continue to circulate. Well, those backup pumps did not run because the generators were offline. So they ended up, there was six or seven reactor cores, but I think the 7 reactor cores. At the 3 reactor cores went into critical meltdown that day, and there was a large escape of radioactive material along with hydrogen gas explosions. Eventually, 4 of the reactors were damaged in this, 4 of the 7 reactors. About 20,000 people were killed by the combination of the earthquake, the tsunami, and the evacuations due to the nuclear accident. But none of those 20,000 deaths were directly attributable to the radiation leakage itself. So yes, there was an escape of radioactive material. Yes, there were hydrogen gas explosions, but they didn't kill anybody. And there's been no known deaths related to this radiation leakage. Now, is there radiation leaking? Yes, there is. In fact, radioactivity is known to be currently contaminating groundwater in the area and ocean waters close to the defunct plant. There have been reports of phenotypic mutations in insects that are living close to the plant. This has not been independently verified, but there may be some reports of radiation-induced mutations in insect populations around the plant. Not 100% sure of that. But yes, radioactivity is contaminating groundwater, and yes, it's contaminating the ocean waters. But people are not dying due to radiation poisoning or anything like that. And it's nothing along the scale of Chernobyl. Okay, so radioactive waste, obviously a problem. Radioactivity is damaging to living organisms, so radioactive nuclear waste has to be stored in special secure locations. The use of nuclear energy produces 3 types of waste. It produces high-level waste. High-level waste is used fuel and control rods, highly radioactive. It also produces low-level waste in the form of contaminated protective clothing. So when workers go in and service the reactor, they have to wear protective clothing. That clothing is low-level nuclear waste. Tools, rags, and other items that are used in routine plant maintenance are also considered low-level radioactive waste. And then finally, we have uranium mine tailings. They are radioactive. The residue that's left behind when uranium ore is mined and enriched is tailings, and they are radioactive waste. They have to be stored securely. Radioactive waste disposal is federally regulated, and high-level radioactive waste has the most environmental impact. So here's a couple of definitions for you. What's a half-life? Half-life is the amount of time it takes for 1/2 of a radioactive substance's atoms to decay. We've talked about this before, but it's time to revisit it because we're talking about radioactive waste. 2 other lesser known ways to measure radioactivity is a becquerel. A becquerel measures the rate at which a sample of radioactive material decays. 1 becquerel is equal to the decay of 1 atom per second. I have never seen the unit of becquerel used on the test, but there it is. A curie is another unit of measure of radioactivity. 1 curie equals 37 billion decays per second. Curie is named after Marie and Pierre Curie, who figured out radioactivity and worked with radioactive materials. They both died, by the way, of leukemia from exposure to high levels of radioactivity, and they did not know it was dangerous. All right. All right, so let's do some math. Calculating half-lives. We've done this before, but again, it's a good time to revisit since we're doing nuclear energy. Strontium-90 is a radioactive waste product that's produced by nuclear reactors. It has a half-life of 29 years. How many years will it take for a quantity of strontium-90 to decay to 1/16 of its original mass? So if the half-life of strontium-90 is 29 years, and we know what the definition of a half-life is, then it's going to take 29 years for it to decay to 1/2 of its original mass. There it is. Okay. It'll take another 29 years to decay to 1/4 of its original mass. Another 29 years to decay to 1/8 of its original mass. And another 29 years to decay to 1/16 of its original mass. So 29 times 4, or 29 plus 29 plus 29 plus 29 is 116 years. So it will take 116 years for a quantity of strontium-90 to decay to 1/16 of its original mass. All right, so now it's our turn. We have 180 grams of a radioactive substance. It has a half-life of 265 years. So after 1,325 years, what mass remains? Well, we've got 180 grams. Oops, I'm moving the slide around. Gosh, I'll keep doing that. And after 265 years, half of that mass remains, because that's the definition of half-life. So after 265 years, we end up with 90 grams, right? So 265 more years, 265 plus 265 is 530 years. So after 530 years, we have half of our 90 grams, which is 45 grams. 530 plus 265 is 795 years. So after 795 years, we have half of our 45 grams, which is 22.5 grams. Okay. 795 plus 265 is 10,060 years. After 10,060 years, we have half of our 22.5 grams, which is 11.25 grams. 1,060 plus 265 is 1,325, which is our goal years. And after that amount of time, we divide our 1125.25 grams, and we get 5.625 grams. So after 1,325 years, we end up with 5.625 grams of our original radioactive substance. And that's just based on the definition of half-life. All right, so what about nuclear fusion? So we've been talking about nuclear fission, which is what we do. We split atoms. What about if we try to join them together? Well, nuclear fusion is the reaction that powers the sun and other stars. It's the fusion of 2 hydrogen atoms into a helium atom. You guys probably don't know the song by They Might Be Giants, but there's a song. You can look it up. There might be giants. Oh, the sun is a mass of incandescent gas. It's a giant nuclear furnace where hydrogen is made into helium at a temperature of millions of degrees. That's how I remember nuclear fusion. Weird as that is. Okay, so fusion would offer an unlimited energy source that requires only hydrogen and produces only a small amount of radioactive waste. Yay, unlimited energy. However, fusion on Earth requires a level of heat input that is 10 times the temperature of the core of the sun. We can't really do that yet. So the heat input needed makes containment of nuclear fusion extremely difficult. And so far, the energy input needed to create that amount of heat is way bigger than the amount of energy that's generated by fusion. So there's lots and lots of laboratories around the world that are trying to get nuclear fusion online, but so far the physics of it are really, really tough. So we don't have it yet. If we achieve nuclear fusion and it can be like scaled up to provide commercially available energy, then the energy crisis and all of our energy needs will be solved pretty much forever, because there's a lot of hydrogen in the universe and we can use it to create our fuel. But so far, it's kind of a pipe dream, and it's not obviously commercially available.